Okay, good morning everyone. Today I will be starting a new topic, that is that of the hydrodynamic bearing design. We have previously seen the rolling contact bearings or the ball bearings. So there the principle of operation is different than what we are going to see here. So these bearings are also called as a sliding element bearing. So as compared to the rolling that happens, that is balls or rollers which are rolling against the bearing race, in the rolling contact bearing, here there is sliding contact. So the part which is rotating, that is for example shaft, which is inside a sleeve, and a shaft sort of slides within the sleeve. These bearings have certain characteristics and certain distinct advantages which make them very significantly useful for applications where there are very high speeds and high load requirements. So in that region, the other type of bearings, they fail. So the rolling contact bearings would fail in those situations. So there these bearings are advantageous. So we'll start today's session with one YouTube video which will explain the basic principles of the hydrodynamic bearings, and some terminologies will be introduced which we'll discuss later. So let me start the video.
Hi, I'm Adam. This is the Machine Tech video blog, and today I'd like to talk to you a little bit about hydrodynamic bearings.
Seems to be some streaming issue on YouTube.
As I've mentioned before, there are two main categories of bearing: anti-friction and hydrodynamic. Anti-friction bearings, which are composed of balls or rollers sandwiched between two rings, are often the preferred method of shaft support in modern machinery. They come in many different standardized sizes and styles, and so it's easy to find off-the-shelf replacements for most applications. But where large, heavy machinery is concerned, the hydrodynamic bearing is the bearing of choice. Sure, they're a little less efficient and they have sensitive lubricant needs, but their design is simple. They can handle extremely high loads, and theoretically, they can last forever. A hydrodynamic bearing is really nothing more than a sleeve with some lube in it that a shaft spins around it. But like all simple things, the devil's in the details, and there are various key factors to consider for each one of these components. The rotating component of the bearing is called the journal. The journal is the part of the shaft which actually rides inside the bearing. Since the whole purpose of a shaft is to transmit power in a machine, it's always made out of a strong material like alloy steel or stainless steel. And sometimes the journal sections of the shaft get an additional extra treatment like chroming in order to improve hardness and wear resistance. The stationary component of the bearing can either be an integral part of the machine casing, or it can be a pillow block, which means that it comes as a separately mounted unit with its own base. Now, sometimes you'll find these solid housings, but more often than not, the housings will be split axially so they can be pulled apart for maintenance. Notice, by the way, the oil groove in the top half, which helps to distribute lubricant throughout the bearing. Now, the inner bearing surface is called a shell or sleeve, and it's usually constructed in 2 or 3 different layers. The first layer is always some kind of strong support material. In this case, it's cast iron because that's what the housing is made of. Sometimes there's an intermediate backing layer on top of the support material. And the final layer is a lining of soft bearing material like copper alloy and aluminum alloy, or most commonly, babbitt. Babbitt is a type of white metal which usually includes some percentage of lead, tin, antimony, and copper. Babbitt is such a common bearing material that sometimes hydrodynamic bearings are referred to simply as Babbitt bearings. But why is the bearing shell made of a softer material than the journal? Well, it's a sacrificial component meant to protect the shaft. If there's ever metal-to-metal contact between the sliding surfaces in the bearing, then the bearing shell will wear before the shaft, and then it can just be renewed or replaced whenever necessary. It's always cheaper to reline the bearing than it is to replace the shaft. And another way that the soft bearing material protects the shaft is by allowing foreign debris or contaminants in the lubricant to embed themselves in the bearing shell instead of scoring the shaft. Despite the relative simplicity of their construction, the physics at play in hydrodynamic bearings require some explanation. Let's start with the machine off. The bearing is designed with a carefully sized clearance or gap between the journal and the sleeve. It won't be much, maybe only the size of a human hair. The clearance in this animation is exaggerated for demonstration purposes. The clearance is filled with lubricant, usually oil or grease, which is just oil thickened with some type of soap to keep it from running out all over the place. The weight of the shaft and other rotating components causes the journal to sit at the bottom of the clearance, and there's metal-to-metal contact. Notice that this means that the clearance is asymmetrical. It's not the same size all the way around the bearing. This will be important when we turn the machine on, but before we do that, in order to understand what happens during operation, we should talk about the third component of a hydrodynamic bearing, the lubricant. Any fluid, including this molasses, is made up of many tiny little molecules held together by intermolecular forces of attraction. When a fluid flows, layers of these molecules slide past one another, attracting and pulling on each other. And this causes resistance to flow. It's like the fluid's internal friction. Most people just think of it as how thick the fluid is, but the technical term for this characteristic is viscosity. Molasses, as well as being extremely delicious, also has a relatively high viscosity. Kerosene, on the other hand, as well as being not delicious at all, has weaker intermolecular forces of attraction and therefore has a relatively low viscosity. But temperature also plays a role in a fluid's viscosity in any given application. When it comes to liquids, an increase in temperature results in a decrease in viscosity, and vice versa. That's where the phrase "slow as molasses in January" comes from. The reason why we care about viscosity in a hydrodynamic bearing is because the same forces which attract fluids to themselves also make them sticky. They're attracted to the surfaces of objects, like the shell and journal in a bearing. When the machine is turned on, the journal begins to rotate. It drags the lubricant around the bearing and jams the lubricant between the two sliding surfaces at the point where they contact. The journal is essentially pumping the lubricant. The pressure underneath the journal begins to rise, and when the journal is spinning fast enough, a lubricant wedge forms which lifts the journal off the sleeve and completely separates the two surfaces. This is where lubricant viscosity plays a crucial role. Too low of a viscosity and the wedge won't form at all, but too high of a viscosity and friction will quickly overheat the bearing. Incidentally, the lubricant wedge also pushes the journal off to one side of the sleeve. This condition is known as full film lubrication. It's like hydroplaning in your car when you drive over a puddle and momentarily lose steering control because the tires are sliding on a film of water. Loads imposed on the bearing are supported in the load zone, and the relatively wide area of the load zone explains why hydrodynamic bearings have such a high radial load carrying capacity. The thickness of the film may only be a thousandth of an inch, but if the bearing was designed with the correct clearance, shaft speed, and lubricant viscosity, and if it's been maintained properly, then there should technically be no physical contact between the two sliding surfaces, and therefore there should be no wear of the journal or the sleeve. Theoretically, a hydrodynamic bearing should be able to run forever without ever needing to be repaired or replaced. In fact, there are some which have been in service for over 100 years. There are a few variations on the plain hydrodynamic bearing which we've outlined here. For example, since the shaft needs to get up to speed for full film lubrication to form, the bearing is especially vulnerable to wear at both startup and shutdown. So the bearings in some very large, very heavy machines have auxiliary hydraulic pumps which actually pressurize the lubricant through oil slots in the bottom of the bearing. This helps to lift the journal off the sleeve. Sometimes these designs are referred to as hydrostatic rather than hydrodynamic. Some bearings are designed with tilting pads equally spaced around the inside of the bearing. The pads can pivot slightly, and each one forms its own hydrodynamic wedge. This helps to stabilize the shaft. Now, normally hydrodynamic bearings can only handle radial loads and are free to float axially. But when the tilting pad design is applied to the face of a bearing and mated to a collar on the shaft, then axial or thrust loads can also be supported. Very effectively, I might add. And of course, oil and grease are not the only fluids used in hydrodynamic bearings. The high-speed spindles and the hard drive from your computer actually ride on air bearings with very fine surface finishes. Well, that's your introduction to hydrodynamic bearings, their construction, the basic operation, and a few of the variations. And that's it for today from the Machine Tech video blog. I hope you learned something.
Okay, so
Hey, I'm Adam. This is the Machine Tech video.
that was some introduction about the hydrodynamic bearing. Now let's discuss the things which were shown in the video. Let me just stop the video and bring in my screen. So we have some quick quizzes for based on the video. The link in the chat box. Okay, so we are set up for the quiz. So we have seen in this particular YouTube video the hydrodynamic bearing, what is the basic principle of operation, and what are the different elements which are involved. So what is journal or the shaft, what is the sleeve, what is the material for the sleeve, and the lubricant. So let's recap. So what are the advantages of hydrodynamic bearings as explained in the video, at the beginning of the video. Okay, so let's look at your answers. Okay, so majority of you are thinking both of the above. So you have to read the second option carefully. So minimum wear and tear is the correct answer. High load carrying capacity in general is right answer, but it is written at low and medium speed. So that is the not advantage but disadvantage, that at low and medium speed it cannot carry high loads. So high load carrying capacity is available only at the high speeds. So only first is the correct answer and second is wrong, and hence third is also wrong. Okay, so that is just, I think we have one more question. Okay, so what is the fundamental principle? As we have seen in the video, the oil, because of its stickiness, it gets dragged into the wedge, which is formed between the sleeve and the journal or the shaft. And that wedge gives the load bearing capacity. I mean, the pressure developed in that wedge gives the pressure building, the load bearing capacity. So formation of viscous oil wedge is the correct answer. The basic name hydrodynamic implies that its load carrying capacity is derived from the dynamic action or from its rotation. So there is no externally supplied pressure in the case of hydrodynamic bearings. It is those bearings are called as a hydrostatic bearing. So we will not be covering that in this particular course, but we'll just know that whenever the bearing design can be done based on externally pressurized system as well. Obviously, they will be costly and they are called as hydrostatic bearings. Obviously, then third is not correct. Okay, let me reset the form. Yes. Okay, so we got some exposure to the hydrodynamic bearing. As we have seen, there are three important components. One is the shaft or the journal, the sleeve, and the lubricant. So let's look into some thing in the next session, that is in the next lecture, we'll see more details about this. But at present, we'll just have overview. So the types of lubricants are three. So one is liquid, which is the most common. So that could be oils, which can be mineral or vegetable oils, or they can be grease. Then you can have the second type of bearing is semi-solid. So the grease comes in this particular thing, and then you have solid. So solid is like powder type of thing. So the most common is graphite. So here there is no paste of paste like thing. So it is just a solid powder that is used as a lubricant. So it can be graphite or molybdenum disulfide. So this is the two most common solid lubricants. Those are used. Of course, they are not will not come under hydrodynamic bearing type. Means the principle of operation will be different. The objective of lubricant obviously is to reduce. First objective is to reduce the friction. In addition to that, they are having some other auxiliary functions because of their presence. And one important function that this lubricant serve is a dissipation of heat. So lubricants, when they are moving around the journal and getting trapped into the wedge and then they are released, part of that lubricant is getting depleted or it gets leaked from the bearing, and while it is getting removed, it also carries some of the heat that is generated because of the friction. So essentially, when you say that viscosity is giving you the load carrying capacity, the viscosity also introduces the friction, and you have to overcome that friction, and as a result, heat will be generated, and that heat will be carried away by the lubricant when it is getting depleted. So not means you have to continuously supply the lubricant so that the part of the lubricant which is getting removed or leaked, it gets replenished, and that leaking fluid, it removes the heat. The third thing is that they have got additives which prevent the corrosion between the two parts. So that is also one more advantageous thing about uh, the lubricants. And they, in addition to reducing the friction, they also reduce the wear. So the particles, the foreign particles which may enter into the system, they will be uh, trapped and removed while the lubricant is moving out. So those are some of the additional advantages that the lubricant serves. So as you can see, lubricant is a key element in this functioning or operation of this bearing. There are three modes of lubrication. They are called as a thick film lubrication, thin film lubrication, and zero film lubrication. The thick film lubrication is the topic of our discussion. So here the film thickness, thick means it is not literally thick. It is still in the level of micrometers, but they are different than the thin film, where the main difference between thick film and thin film is there is no metal to metal contact. No metal to metal contact in the thick film, while in thin film, the metal to metal contact would happen occasionally. And in zero film, there is direct metal to metal contact. The thick film bearings which we are talking about, they are of two types. One is hydrodynamic, that is there is no external pressure supplied to the oil, and hydrostatic, where there is external pressure is being supplied to the oil. So there is no need of, means although the hydrodynamic action will be there, but external pressure would provide the majority of the load bearing capacity rather than the hydrodynamic action. The thin film is where you don't require that high load carrying capacity. So typically they are used in machine tools for sliding operations. So wherever you have the tool post which is moving on the frame of the lathe, so that kind of sliding will be a example of thin film sliding. The zero film sliding is where there is direct metal to metal contact. So they are usually not for the load carrying components, so components which are having very less loads like door hinges and other places. That is where the zero film lubrication would be used. So there is a direct metal to metal contact. So you can get more information about this in the textbook, but essentially the main points I have covered here. Based on the geometry, the hydrodynamic bearings can be classified into three types. One is the full bearing. So full bearing is where the journal or the shaft is fully surrounded by the sleeve. So sleeve is of full circumference. So this is the journal or the shaft, and this is the sleeve. So the sleeve is throughout the circumference of the shaft, fully surrounding. So that is known as full bearing. So full bearing will have the maximum load carrying capacity. The partial bearings is where the sleeve is of partial size. So you will have the journal which is rotating, and the sleeve will not cover the entire circumference of the bearing. So these are the partial bearing. In this course, we will be studying only the full bearings. The partial bearings typically they are used in railway cars, that is the wagon cars, at the wheels. So in this case, you have to continuously supply the oil because it gets depleted through both circumferential side as well as length side. In the full bearing, there will be the leakage will happen in the lengthwise direction. So if this is the shaft and the bearing is here, so in the full bearing, there is the oil is supplied at the center and it gets distributed over the length, and the leakage will happen through the sides. So there will be flow of liquid in circumferential direction as well as in the axial direction. So axial direction, some leakage will happen. Circumferential direction, some flow will be taking place. Whereas in case of partial bearings, in both circumferential direction as well as the axial direction, there will be leakage. Thrust bearing is based on the orientation of the bearing. So if the journal is vertical, so in that case, you will require an arrangement where the oil pressure needs to be generated at the bottom of the shaft. So that is a thrust bearing design. So part of that, using the pressure pads, what was explained in the video, is type of thrust bearing for which hydrodynamic bearings will be used. We'll be discussing in this course only the full bearings, which essentially cover the fundamental principles based on which the other two types can be derived. Okay, so let's move ahead. So one of the important things that needs to be established in the design of hydrodynamic bearings is establishing the coefficient of friction. One thing is we need the load carrying capacity, which comes because of the viscosity, but the viscosity also brings us the drag force or the resistance force to the rotation of the shaft. So in order to determine, and this resistance will be overcome by whatever prime mover you are giving to your shaft, and when it work is done against the frictional force, it will be converted into heat. So as a result of which your bearing lubricant will get heated up, and that heat needs to be properly dissipated. So in order to estimate the amount of heat which is getting generated, it is important to get the friction factor. So Petrov did some experiment and theoretical work in year 1883 to determine the friction coefficient for hydrodynamic or the oil type of bearings. So the case that he considered to derive the formula that we see here, this formula is important in the sense that it covers some of the important parameters that are valid for the hydrodynamic bearing. The case that he considered, it was not strictly a hydrodynamic bearing, in the sense there was a sleeve and there was a journal, and he considered this sleeve to be subjected to load which was very small. So there is a small amount of load or light loaded bearing is what he considered, whereas we are talking about high loading conditions. Uh, but the important part is that the equation that he developed that reveals some of the major parameters that cover this particular hydrodynamic bearing design. So when the shaft is rotating and in between you have the fluid or the lubricant is filled in this particular space. So that is the place where the lubricant is there. So if I draw the top view, you will see this is the sleeve, and inside that, just exaggerated, is the journal or the shaft, and in between there is the lubricant film which is there. So in this particular analysis, Petrov assumed that there is no eccentricity. We have seen in the hydrodynamic bearing there is, because the wedge shape takes happens because of the eccentricity of the shaft with respect to the sleeve. In this particular analysis, everywhere uniform gap between the shaft and sleeve is assumed, and whatever external load is getting acted upon, it gets resisted by the pressure which is developed within the lubricant film. So in order to get this pressure generated, or other his interest was in the frictional drag which is getting generated. The basic principle used was the Newton's law of friction, so or Newton's law of viscosity. So when you have two bodies which are sliding with respect to each other, so there is, let's say, a plate which is moving at velocity v, and you have got a gap h, and in between there is a fluid, and let's assume this bottom plate is stationary. Then the frictional drag is, or the force which is created, which is exerted on both the top plate and the bottom plate because of the viscous drag here, which you have learnt in fluid mechanics, is given in terms of mu a into dv by dh, where h is this vertical direction. So let me call it y, dv by dy. So if this is y and this is x axis, so the velocity gradient multiplied by area of these plates multiplied by the mu is the absolute viscosity, you get the frictional drag which is getting created. Now this frictional drag will act at every, means if you consider small sections this lubricant to be made up of, so this drag force will act. So if this is the rotation direction of the shaft, opposite to that would be the frictional force will be generated. So at every sector, if you imagine this film lubricant to be made up of small radial sectors, so every sector will provide some force which is governed by this particular equation. So df equal to dA and dv by dy in the radial direction. So that way the force generated, and this force multiplied by radius will give you the torque. So the torque, the frictional torque which will act on this particular bearing, so empty friction, can be determined in terms of df multiplied by the radius. So note that this df will consist of viscosity and other velocity profile parameters, and this he matched with the equivalent. So this f is an equivalent coefficient of friction when journal is rotating, So F is the equivalent friction coefficient. So multiplied by the load W which is acting. So that will give you the net tangential force. So the net tangential force will be mu, sorry, not mu, the friction factor times the load which is acting on it. And since that we are talking about the torque or the moment, so here also we will be multiplying by R. So essentially we get this particular equation. And if you develop this both the sides, finally you will arrive at the equation which is shown here as the Petrov's equation. You can see the derivation part in the textbook. I'm not covering it here. It is fairly simple. And what important thing to be noted in this particular formula is he one of the parenthetic term which is given here mu ns by p was further studied, and it was found that this particular term is important, and that is called as a bearing characteristic number. And we'll see in the next slide that based on this characteristic number, whether the thin film lubrication will happen or thick film lubrication will happen will be decided based on this particular number. And another important thing that this particular equation that Petrov developed revealed, which was later on studied, is I'll just rewrite this equation in a particular form. So I'm multiplying by R by C to the both sides. So I'll get 2 pi square R by C square multiplied by mu ns by P. So the term which we get here is known as Sommerfeld number. And this is a very important parameter in the design of hydrodynamic bearings. Now, why this parameter is important is look at what all things are covered in this particular parameter. It essentially covers all the design parameters those are required for establishing the size of hydrodynamic bearing. So let's see what parameters this particular number, Sommerfeld number contains. The one is the R. R is the radius of this particular shaft. So that is the diameter of the shaft. So that is obviously an important input. The C is the clearance between the shaft and the radial clearance between the shaft and the sleeve. So this is again a parameter which a designer of hydrodynamic bearing needs to be knowing. Then mu is the absolute viscosity of the lubricant, which is giving this load bearing capacity to this bearing. So mu is selection of lubricant oil will be one more design parameter which gets captured in the Sommerfeld number. Ns is the rotational speed of the shaft. This S stands for, instead of RPM, it is in per second. So revolutions per second. So that is the unit. So that is why Ns is written here. So N is the rotational speed, which is based on your requirement. And P is the load divided by the projected area of the bearing. So D is the diameter of the bearing and L is the length of sleeve. So L into D is the projected area on which the shaft is resting and getting the resistance. So that is known as the bearing pressure or unit pressure. So that is another important parameter. You need to decide what length of sleeve to be given. So you can see that in this particular single parameter called as Sommerfeld number, all the everything that you require to design the bearing or which you need to establish in the design of the hydrodynamic bearing are getting captured. So the Petrov equation in that sense is important, although this equation per se is not uh, useful for the design, but the study revealed the important factors which will influence the hydrodynamic bearing, based on which further analysis was done by Reynolds, and that we'll be studying in detail today. Okay, so as I said, this mu ns by P is called as a bearing characteristic number. So here you see a graph where the bearing characteristic number is on the x-axis and the coefficient of friction is on the y-axis. A particular study, again a series of experiments were done by Mackey in about 30-40 years after the Petrov's equation, and he found an interesting correspondence between the bearing characteristic number, which is defined here on x-axis, versus the coefficient of friction. So assuming that you have selected mu and p, that is the bearing sleeve size are decided and the lubricant is decided, as you increase the speed, that is ns, you'll find that initially the coefficient of friction decreases. So there is a decrease in coefficient of friction, and after some time there is an increase in the coefficient of friction. The point where the minimum value of coefficient of friction is reached is called as a K, or it is called as a bearing modulus. So bearing modulus is an important parameter in the sense that if you are operating to the left of this K, that means your characteristic number is smaller than K, then you will find that it falls in the regime of thin film lubrication, which is essentially unstable in the sense there is intermittent metal to metal contact is happening, which is undesirable, especially for high load applications. So you never want to work in this particular region. And when your characteristic number is higher than the bearing modulus or K, in that case, you gradually get thick film lubrication. As you move more towards the higher values of characteristic number, you will get higher and higher friction coefficient. That means your resistance to the motion will be increasing, but at the same time, you will get more and better load carrying capacity. So usually uh, the operation is done in about 5 to 7 times K is the operating bearing characteristic number which is used, so that you are operating somewhere in this particular regime where you get a proper thick film lubrication with no metal to metal contact. So that is known as a stable operation. Stable in the sense there is no metal to metal contact, so there is no noise and wear and tear. If you are having high fluctuations in the load and more impact conditions, so you are using this particular bearing in some tool which is having intermittent impact, so you are doing some crushing operation or braking operation. So in that case you need to use higher values. So in that case about 10 to 12 times K is the factor, which is the characteristic number is where you operate in order to get a properly working hydrodynamic bearing. Okay, so that is the background based on which the further study for the design of hydrodynamic bearing is done. So we'll look into the further part of the design. Okay, so any questions at this stage about the design of bearing? Okay, so now let's look at how this bearing design is to be done. So for that we have to understand that the main way of operation of bearing we have to understand. I think it is better if I show through design data book. Okay, so this was what was explained. I'm opening now the design data book pages. So this particular phenomena of how the bearing works is explained in this particular diagram. So what you see here is the three stages. So initial stage, there is a metal to metal contact in hydrodynamic bearing. As the speed increases, the journal slowly rides over the sleeve, and at the same time the more oil gets sucked in the gap between the shaft and oil. So as a result of which the shaft moves again in the opposite direction and finally settles at one position where there is equilibrium between the forces which are generated in the oil wedge. So essentially the forces which are generated in the oil wedge is the pressure. So actually this particular wedge acts as a pump. So oil is getting sucked from the larger end of the wedge and it is getting pushed out from the smaller end of the wedge. So this in between them there is a increase in pressure or variation of pressure which gives the load bearing capacity to this particular bearing. So to bring back uh, to our discussion. So if this is the sleeve, and during operation the bearing settles down somewhere eccentrically with respect to the sleeve. So this is the center of the journal, and this is the center of the shaft. So in between them there is uh, a zone where the pressure starts building up. So pressure starts building up at one particular point. So at every point there will be some pressure which will be generated. So if I plot the pressure variation across the wedge, you will find that the pressure gets distributed across this wedge as shown here. And if you take vertical, so each of these pressure component, if you consider small elements over the surface of the sleeve or surface of the shaft, they will be pushing the shaft in the direction of the pressure. If you consider all the vertical components of this pressure force, that will match with the load which is coming on the journal. So that is what gives the load bearing capacity to this particular hydrodynamic bearing. So it is important that you establish what is the variation of this pressure which gets built up inside the oil wedge, and in order to determine that you need to understand how this particular bearing works, and that study was done by Reynolds in the same time about maybe 2-3 years after the Petrov equation was developed. So he did an analytical study and developed a governing differential equation, which gives us the variation of P. So it is a partial differential equation which relates P versus the velocity distribution in this particular oil wedge. So if you look into this oil wedge, so you'll find that if I zoom this particular part, so this is the sleeve and this is part of the shaft. So the shaft is moving at some RPM, because of which it has got some velocity which I am calling as capital U, and the sleeve is stationary, so the air velocity is 0, and at the upper point the velocity is equal to capital U. So in between them there is a variation of velocity, so the velocity distribution will be different. So at the top point it will be U, bottom point it is 0, but in between it could be linear or it could be concave or it could be convex. So the relationship between pressure and velocity is the one which needs to be established. So that is the first step towards. Finally, what we want is this pressure distribution. So we can once we get this pressure distribution, we can calculate how much load can be resisted by that particular pressure. So the first step is to establish the relation between pressure and the velocity field, and then this velocity can be eliminated and you can directly get the variation of pressure. So the final form of the differential equation is a relation between pressure and theta or what the equation refers as a x direction. So x direction is the circumferential direction. So with respect to x, so p as a function of x is what we are trying to establish, and that is what study Renault did. And in this week's tutorial, we'll be covering the derivation of Renault equation. So in today's session, we'll directly look at the equation and just understand what is the outline, how this equation can be derived, and then we'll see how that differential equation can be solved or is solved, and how to use it in the design considerations. So in the next, we will see the Reynolds equation. Okay, so the Reynolds equation, it has some assumptions, so we'll discuss that. So the final form of the Reynolds equation looks in this particular manner. So where P is the pressure distribution which we are interested in, X is the circumferential direction, and H is the height of the wedge. So at every point there is, so I'm just zooming this particular figure. So H is the local wedge thickness, and X is the circumferential direction. So that is the axis that we are defining. So finally, we get an equation which you are going to derive in this week's tutorial. We will see final form. We will get this particular differential equation. If you solve this differential equation, you will get P in terms of X, and that is how the load bearing capacity can be determined. Now, before we go into the details how this derivation is done, or some outline as to how this derivation is to be done, let's look at some of the assumptions which this Reynolds equation is based on. So the equation that we are talking about is based on some assumptions, so which we'll discuss now. Okay, so the first assumption is that lubricant is of certain types. So let me maximize so that you can read properly. So the first assumption is that I just kept some places blank so they can tell me what should be that assumption, which is you can guess very easily. So lubricant is assumed to be a certain fluid type which obeys which law? So can you tell?
Newton's law of viscosity.
Newton's law of viscosity, which we just now discussed, which we discussed during the Petrov equation. Okay, the second assumption means from this statement it is difficult to guess, so I will give a clue that the lubricant can be, I mean, this particular property of the lubricant can be defined in terms of the difference. There is some property which the liquids have, which the gases don't have. So some property of liquid which is there for lubricants, for gases it is not there. So that is the word we are looking here. So the assumption in the derivation is that lubricant is having some property which is property of liquids as compared to the property of gases.
Hello, sir.
Incompressible.
I did not listen. I did not get incompressible. That's right, Mukul. So the lubricant is assumed to be incompressible. So that is the second assumption. That's right. Okay, then there are different forces which act on the particles of the lubricant. So the equation is derived based on we consider a small particle in the lubricating film, and then we calculate what are the forces acting on that particular particle. So that is better. So what forces are considered out, and one particular force is ignored. So we have to you have to tell which force is ignored. Before that, I will just explain what forces we are considering. So the force on the particle which is there inside the wedge, so this is one particle on the wedge of size dx and dy. So this particle is subjected to pressure. So obviously the pressure into the surface on which it is acting. So on one surface pressure is P, on other surface the pressure is P plus dP by dx into dx and its surface area. So pressure force is what we are including. The second is the viscous drag. So this tau is the shear stress which gets generated in the fluid because of the viscosity. So viscous forces also we are considering. So these two forces we are considering, and there is one force which we are ignoring on this particle. So what is that force is what I want you to tell. I want you to tell. So which forces are negligible could be an assumption of Reynolds. So on this particle, what other forces are there which we are ignoring?
So the weight.
Body force.
Okay, somebody said weight. So weight is one part. So that is gravity or the weight of the particle is ignored. Okay, that is correct, but that is not. There is one more significant force or more significant than gravity, which is ignored, which Mukul said as body force. So can you elaborate what is body force? I think Mukul or somebody said body force. I just want to understand what do you mean by body force.
So when I said weight, I was meaning to say the loads of the shaft.
Oh, no, no. We are talking about the forces acting on the lubricant particle. So this is a particle inside the lubricant, which is trapped inside the wedge. So on this lubricant, we are not talking about the metal part, not the load. In the sense the load get generated, that's right. So that is the pressure force. So ultimately when you reach here, there is pressure. So the pressure being equal in all directions. So once we find this horizontal component of, or not component, the P value, the P is same in all directions. So when you reach at the top end, whatever value of P is there, so there will be P1 here, P2 here, P3 here, and so on. The distribution will be there. So based on that, the load can be calculated. So this load is not is getting converted into pressure, and then it is acting on this particle. So there is, okay, so let me add that there is a pressure on top and bottom. So there is one more assumption about this load effect in terms of pressure. But this particular assumption, that assumption will come later on. First, we'll talk about the assumption about what additional force is there, which we are ignoring. And that, okay. So somebody said body force. So can somebody just explain what is the body force?
Sir, weight of the lubricant.
Yeah, that's what I said. Gravity is gravity. What I meant, what Prasad meant was something different. What I understood is the gravity or the weight of particle is ignored. So that is correct. But that is in addition to gravity, there is something else which is the force which is higher than gravity force, which is ignored. So what is that force?
The inertial forces.
Inertial force. Yeah, that is more accurate description. So why inertial forces would come?
Said due to the volume, like it would resist the motion.
Okay, it is because of the acceleration and deceleration if it is happening. So mass of that particle into whatever acceleration it has got, that is the inertial force. Or since it is now going in a circular motion, so there will be centrifugal force which will be acting on this particle. So those forces are neglected. So they are much higher than the gravity or the weight of that particle. So those, but they are insignificant as compared to the pressure force which we are talking about. So inertia forces are neglected in this particular analysis. Then some property of lubricant is assumed to be constant. So this you should be able to guess easily. So what property of lubricant is assumed to be constant? Sorry, I did not hear Jay.
Viscosity.
Viscosity. That's right. So we are assuming that throughout inside to outside, the viscosity remains constant. What could be the reason why the viscosity may change from one end to the other end?
So temperature difference.
Temperature difference. Since there is a viscous drag, the fluid which is entering would be at low temperature, and when it passes through the wedge, because of the drag it is experiencing, it will get heated up. So the one which is coming out of the wedge will be at higher temperatures, and viscosity is a function of temperature. So that effect we are neglecting. Okay, the pressure is assumed to be constant in one direction. So now let's define the axis. So here I said that circumferential direction is x direction. The radial direction is y direction. So in the front view, this is the length of the sleeve. So this is the sleeve. Uh, so the y direction is in the radial direction, and z direction is along the length of the sleeve. So there is a x direction, y direction, z direction. So in which direction pressure is assumed constant? Or first you tell in which direction pressure is assumed to be varying. There is only one direction in which pressure is assumed to be varying, and other two directions it is constant.
X direction.
X direction. So as we momentarily see in the previous slide, so there is a P plus dP by dx. So that means X direction pressure is varying. So as we have seen, the circumferential pressure distribution would be there. So in the X direction, there is a variation of pressure. So in Y direction, that is in the radial direction. So so from bottom end of the wedge to the top end of the wedge, we are assuming that pressure is remaining constant. So there is no variation of pressure in radial direction, as well as in the Z direction, that is across the length of the sleeve. As you can see here, the sleeve is open to the atmosphere at both the ends. So that means pressure here cannot be, it has to be equal to the atmospheric pressure. So towards the end, the pressure would not be same as that which is there at the edges in the wedge. So the assumption that Renault did in this particular development is that pressure is constant across radial direction. So that is one assumption. And second is the sleeve is infinitely long, so that there is no variation in the Z direction as well. Across the length of the sleeve also there is no direction. So pressure is constant across radial and longitudinal direction. So that is assumption. Then shaft and bearings are some property. So both of these are metals. So what property you think? So shaft and bearing are assumed to be
Rigid.
rigid. That's right. What would be significance of that assumption? What will happen if they are considered flexible?
Like we are ignoring the deformation, if any.
Right. So if the deformation happens, then this wedge geometry will also keep on changing. So here we are assuming that wedge geometry can be determined simply by clearance. So once you know what is the clearance, you can determine by on drawing board, you can determine what is the wedge geometry. Means analytically also the two circles which are eccentric to each other, what is the gap, equation of gap versus the theta can be determined. So that is assuming that both our circles remain circle. If one of them becomes deformed, then the wedge geometry will be different. So that effect is ignored. There is a continuous supply of, so this is easy to guess.
Lubricant.
Lubricant. So that is the only thing which is getting supplied. Okay, this answer I have already given. So there is, okay, the analysis that we are discussing here, the derivation what we are going to discuss, that is called as a 1D formulation. So the differential equation has got only x term. So there is no y and z term. So if the y term is there, z term is there. So sorry, there is a 2D formulation of Reynolds equation and there is a 1D formulation. What we'll be discussing here is a 1D formulation, which is easier to understand. And there is a 2D formulation, which is given in the textbook by Bhandari, which is a little more complex to derive. So here we are assuming that there is no variation in z direction. So the bearing is infinitely long. So in that case, this particular equation is valid. If the bearing is, if you are considering the variation across the z direction, then you get another form of Reynolds equation, which is given in 2D. So in this case, in addition to this x term, there is a variation in z term is also included. So this is called as a 2D form of Reynolds equation. So we are discussing here 1D form. So no flow in y and z directions for 1D formulation. So which already we said here. So radial and longitudinal are y and z directions respectively. Okay, so the full derivation of the Reynolds equation we'll be doing in this week's tutorial. So there will be, we'll discuss more of this particular formulation. So what we are doing here is essentially we are developing, the Reynolds has developed the governing differential equation, which relates the pressure variation versus x. So if you solve this equation, what you will get is pressure in terms of x or pressure in terms of theta. And once you get pressure in terms of theta, then on the shaft, you can plot that pressure variation. So at every point, the pressure we know. And as I said earlier, you take vertical component of all pressure forces on the on this particular circumference area that will be matching with W. So that is what essentially would be done once you obtain this P of X. So solving this differential equation is not that simple as is there. Means we'll stop at the derivation of this equation. Solution of this equation is of this partial differential equation is more complex, and that was done by Sommerfeld somewhere in 1930s. So Sommerfeld is the one which solved this equation, not this particular 1D equation, but the 2D equation. So this is two-dimensional partial differential equation, which solution the Reynolds, the Sommerfeld obtained for two cases where length is infinity and length is very, very small. So for these two situations, he could find analytical solution. That means direct, he could found the function which defines the pressure variation for when length is infinity and length is very, very small. For finite element length or finite length of the sleeve, the solution, analytical solution could not be found out. So that particular solution for finite length of the sleeve, which is practically more relevant because we never will have very long or very short bearings. We'll have some reasonably long bearings. So for that, the solution, analytical solution to this particular equation could not be found out unless till the time about 1930s, it is 1940s, where using numerical methods, solution was found out, and that solution was found out by two scientists. So they are Raymond. So that solution is named after them. That is called as a Raimondi and Boyd solution to Reynolds equation. So this particular solution is available in the tabular form or chart form. So what this equation, it doesn't give you directly pressure variation in terms of x and z. So that is what is expected, means that is what you think you will obtain as a solution to this equation. The solution is represented in terms of a series of non-dimensional numbers, which are shown in the table below. So this Riemann-Boyd solution is available in two forms. One is a table form and another is a chart or nomogram form. Both are available in the design data book, but we'll be using the table form. It is more convenient to be used. So let's look at how to use this particular solution, because this solution is the one which we need in order to design the bearing. So designing a hydrodynamic bearing means that in general, you know what is the diameter of the shaft. We know at what RPM it is moving and how much load that shaft has at the reaction point at the bearing location. So in order to size the bearing, so by what we mean by sizing the bearing, we have to decide how much clearance you require between sleeve and the bearing, and what is the type of oil to be used, what is the viscosity of the oil to be used, and the third thing is what should be the length of this bearing. So that that is the third parameter. So these three things you need to decide. In order to decide these particular things, the solution is presented in a particular fashion. So that is what we will see. The solution is in terms of a series of non-dimensional parameters. Each row of this table, it represents a solution to the Reynolds equation. So all of these parameters, they satisfy the Reynolds equation for a particular combination of all the design parameters that we have seen here. So the first, let's look at this particular table and then look at the various parameters which are there. The first parameter is length to diameter ratio of the sleeve. So this particular parameter is something. So the first solution is given for length to diameter ratio of infinity. That is an infinitely long bearing, which is the assumption which is made in the Reynolds equation. And then you have more series of solutions corresponding to L by D equal to 1, L by D equal to 0.8, and so on. So for different L by D ratios, the solution is available. The solution is available in terms of some non-dimensional parameters, which we'll see one by one in the next discussion. Let's just recap something related to this particular solution in terms of a quiz. So we have a quiz coming up. Okay, so let's see what answers you are getting. Okay, so it is the answer to this question is sort of ambiguous. That means you have solution, analytical solution is available only for very long bearings, L tending to infinity, or L which are very short, which are tending to 0. So for these two cases, the solution is available. So if you consider not yet determined as an absolute term, so that is false. So some solution is available, but not all L by D ratios, the solution is not available. So that uh, this particular thing, in my interpretation, the answer to this question is true. It can be contested, but the answer which I think is false. That is because some solutions are available. It is not that in entirety solution is not found out. Partially, for some situations, analytical solution is available. Now let's look at the Remondino and Boyd solution to Reynolds equation and understand what are the different non-dimensional parameters which are given there. So for that I will open the design data book. Okay, so let me open up the Remondino and Boyd table. So the in the design data book, the table would look something of this type. So these are the parameters which we are trying to understand. So each row of this particular solution is satisfies the Reynolds equation. So here L by D equal to infinity, corresponding to that there are different rows. L by D equal to 1, there are another set of rows. L by D equal to zero 0.5, another set of rules, and so another set of numbers, and so on. So what are those columns is what we'll understand. So I'll just minimize this. Maybe zoom a little more. Okay, and here we'll look at the description which is given in the further pages of the design data book. Okay, so the first parameter that you see here is epsilon. So epsilon is defined here as the eccentricity ratio. So where my cursor is, so this is the eccentricity ratio, which is the first or the second column. The first column is L by D ratio, which is length to diameter ratio, which we'll be discussing later on how to decide L by D ratio. Once you know the L by D ratio, and you require two of this, any two of the numbers to be known in order to determine the solution row. So for example, you should know L by D equal to 1, and then you should know that eccentricity ratio is something or Sommerfeld number is something. So based on that, you can determine which row to be decided, or between which two rows you have to do interpolation. So we'll see at the design calculations in the next lecture. At this time, we'll just look at the different, these are known as performance parameters for the bearing, or the solution parameters for the bearings. The first parameter is eccentricity ratio. So it is defined as the eccentricity divided by C. So eccentricity is nothing but the, if this is a sleeve center and this is the exaggerated shaft center, the distance between them is the eccentricity E. So that divided by clearance, the clearance is the radial clearance between the two. So the shaft and bearing are having different diameters. If you find the radial gap between the shaft and the sleeve diameter, so that is the C. So E by C is the eccentricity ratio. So that is the first parameter that we are discussing here. Okay, the second parameter is H naught by C. The H naught is the minimum film thickness. So let me see if how the figures so that it can be better explained. Okay, so this figure will first we'll look at the geometry parameters so that discussion would be easier. So second parameter that we are looking here is H naught by C. So the H naught here is the minimum film thickness. The minimum film thickness, as we know, in the wedge, the film thickness varies. So at one point, the film thickness is minimal, and that is called as a H naught. So that H naught needs H naught divided by the radial clearance between shaft and sleeve is the one which is the second column which we are discussing here. So first column was eccentricity ratio. Second is H naught by C. The third one is called as the theta A, which will come discuss later on. The most important parameter is the Sommerfeld number S. So let's go into the Sommerfeld number explanation. So we already discussed Sommerfeld number few in the Petrov equation discussion. So here we'll again revisit that. So as you can see here, this is the equation for Sommerfeld number. So it is R by C the whole square multiplied by mu ns by P. So where R is the radius of the shaft. So this is R, where on the left hand side figure I'm just pointing out what is R. C is the clearance, that is capital R minus small r is the value of C. So that is the radial clearance. Mu is the viscosity of the oil. Now as we have seen, the temperature of the oil increases. So in this particular solution we will also come to know how much is the temperature rise of the oil. So the viscosity of oil is given in terms of temperature versus viscosity. So if you know what is the inlet temperature and outlet temperature, the two viscosity values would be known to us. Average of that is taken as the viscosity to be considered in the design calculations. So this mu is the viscosity of oil, which is dependent on the temperature, and the temperature is dependent on the solution. So there is one more factor which gives us how much will be temperature rise. Ns is the rotational speed of the shaft in terms of revolutions per second, and P is known as the bearing pressure, which is the load which is acting on it divided by length of bearing divided by diameter of bearing. So using these parameters, the next parameter, that is the Sommerfeld number, is getting determined. So let me go back to the table. Okay, so S is the Sommerfeld number we just now discussed. Okay, in the same parameter, this P value is another thing, that is a unit bearing pressure. So unit bearing pressure is defined as W divided by L by D, which I just now explained. The phi is called as a attitude angle. So this attitude angle is the angle at which the minimum film thickness exists. So if you join the shifted center of the shaft with respect to the original center of the shaft or the sleeve, so that particular, I mean, this is the center of a sleeve and this is center of shaft. So if you join them together, it will make an angle which is the attitude angle. And at this particular location, you will find that the film thickness would be minimal. So that location is given by this phi. In our most of the calculations, we don't require this particular parameter, but since it is appearing in the solution I'm giving here. The third important factor is the friction factor. So coefficient of friction variable. So if you remember the Petrov's equation, this is, we modified the Petrov equation in order to make its left hand side equal to this F into R by C. So F is the friction coefficient which will need in order to determine how much heat is getting generated or how much additional power you require in order to drive the shaft over and above whatever load the shaft is taking. So that is for that purpose we require this friction factor. The next factor is known as flow parameter. So that is Q divided by RCNS into L. So here the Q is the total flow. That means whenever you are having this bearing which is operating, you are supplying some fluid here. You need to provide some amount of fluid which is getting leaked out. So as we have seen, some flow will leak out in the longitudinal direction. So that is called as that is denoted by QS, and the quantity Q here is consisting of, there is some flow which is getting recirculated. Let's call that as Q dash. So which remains inside the bearing and it keeps on recirculating around the sleeve, and there is some quantity QS which is additionally supplied. So at the entry point you have Q dash plus QS, and at exit point you have again back to Q dash. So Q dash is constantly revolving and QS is something getting licked up. So this Q is Q dash plus QS. That is a total oil quantity which is entering into the wedge. So that quantity is given by this particular ratio. So here the R, C, NS and L we have already discussed. So those things are known. The important quantity, how much oil is to be replenished, is the thing which you require. So that is the next ratio, that is Q by QS. So QS is the quantity which we are interested in, because that much oil we have to supply during the operation of the bearing. So that would be given by this further column, that is Q by QS. Then we require how much will be temperature rise in the bearing. So that is given by the next column, that is rho Cp delta T by P. So this is the temperature rise factor. So this allows us to calculate how much is the temperature rise, which will help us to select the oil. So at that temperature rise, knowing the ambient temperature, we know how much is the maximum temperature of the oil. So in that temperature range, which oil is suitable, that will decide based on the properties of the lubricating oil which are given in the design data book. So that is the next factor. So next is P by P max. So the pressure is maximum. We know that pressure is maximum at one particular time. So the P what we are calculating is the average pressure. So the P is not the real pressure distribution. This is simply W divided by projected area. If we want to know what is the maximum pressure, so there is P max which occurs at one particular location, that is given by this particular non-dimensional parameter. And there are the two angles, so where the wedge begins and where the wedge ends. So those two angles are defined by this two theta values, which are given position of the maximum film thickness and position of the lubricant film ends. So P max, PO, these are the two angles, and theta A is somewhere which appears in the beginning. So theta is something which we did not, I did not discuss at that point. So that is the angle from the line of centers of the start of lubricating file. So it is explained in the figure. In the design calculations, we don't require this particular numbers. They would be required more from the operation point of view, how much is the width of this wedge and how it is varying. For our design calculations, we don't require this particular set of parameters. So that is where we will stop for today. And in the next lecture, we'll take some numerical examples, because I think it is confusing at this particular stage. So just remember that the table gives the solution to the differential equation, and how to use this particular table, which consists of so many parameters we just now saw, we'll consider in terms of some numerical example, which will make the things more clear. Okay, any quick questions if anybody has? Otherwise, we'll stop here for today. So I'm stopping the recording.